All right, guys, I'm going to go ahead and share my screen here. And I probably have about 5 or 6 problems that we'll work through tonight. I'm going to encourage people as well to work through problems that I already have a video solution for. So let me actually, before I share my screen on my iPad, share my screen here just to give people an idea of some other problems that would be helpful to kind of work through. Sorry, somebody just peeled out in front of our house here. All right, share my screen. All right, so, and I know I went through this in class already, but just to highlight, integrated rate law is this last skill that we worked on. Integrated rate law is sort of embedded in things that we do here with nuclear decay processes. So there was a couple of problems that we could practice here. Keep in mind, if you see a nuclear decay equation, we know that that's first order. So that's one of those things you have to know. Now, again, I told you guys for your quiz on Wednesday, I will tell you in the question prompt what the order of the reaction is. So those are a couple you can continue to practice. We're going to actually have a couple that we'll practice here that are nuclear decay processes. We treat them exactly the same as we treat any first order process. So the skill that we worked on today was integrated rate laws here. So there's a few practice problems here. This is a first order integrated rate law problem. Here's another first order integrated rate law problem. And then there's a first order integrated rate law problem. That's what we call a molecular scene, where you actually look at a picture to get some information. Now, the challenge with all of these practice problems is they are all first order integrated practice problems. So I would encourage you to practice or to look at this. Here are some extra practice problems that include 0, first, and second order kind of prompts. So how these things work here is you can click on, for example, this link here, and this will open up a slide deck that basically has all of the problems kind of written here for you. Okay. If you click on this part, that will actually give you the worked out solution, the key. So again, clicking on this, you'll see that you actually see the worked out key for these problems. So I encourage you, don't look at that until you try them on your own. Okay. And then the other part, this is actually a link as well. So if after you've looked at the key, you don't quite understand how to work through the problem, you can click on this and it's going to take you to a YouTube video, okay, which actually walks through me solving those problems. So it's actually how I made that key for what you'll see there. So you're going to see not only integrated rate law problems, but remember there was that list of things that I put on the board today. There was writing and using rate expressions. There was thinking about nuclear decay processes. I was thinking about writing and using rate laws. There was using the method of initial rates to determine a rate law. And then tonight and today during class, we did more with integrated rate laws. So this sort of piece right here is some extra problems that work through all of those different skills. Okay, so you can use this again for practicing things that you'll see on the quiz on Wednesday. And then these are just some Blackboard quizzes. When we had to do things last year, kind of, we weren't allowed to have paper or anything. I had to do everything on Blackboard. This is how we did quizzes, is it was multiple choice Blackboard quizzes. We took them in class, but I thought this was a great opportunity just to give you guys some extra practice. So these are basically going to be, if you wanted to do some extra integrated rate law problems, you can click on this. There's no credit for these. You'll get a score, but it's not part of your Blackboard. But again, you'll see a prompt here. These are all problems that are written, in this case, just using a generic reaction. So for these, you can work through the problem. You can take a guess at what you think the answer is. You can submit your answers and you'll get instant feedback as to whether or not your stuff is correct. So all kinds of ways that you'll be able to have some practice, in addition to obviously what we're going to do tonight. So I wanted to just take a minute and make sure that everybody sort of sees how things are set up here with Blackboard. I'm still in the process because this is new compared to what I had last year. I should have it released later tonight, if not first thing tomorrow morning. The same sort of structure and format for our next learning unit, which is on equilibrium. So I'm going to pause there for a second, see if Sarah, either you or Elias have any questions on anything so far. Elias, you can either unmute yourself or you can feel free to type something in the chat. Go ahead, Sarah. I see you're unmuted.
Oh, nope, no questions about the practice stuff.
Okay, very good. Elias, anything from you?
No, I'm good.
Okay, all right, so let's go through our first problem here. And I indicated to you guys that the first problem that I was going to work through was going to be, I gave you the prompt at the end of class today. So, if you haven't had a chance to work through this, that's totally fine. I'm just going to, with the two of you that are here, I'm going to ask you to respond in the chat that tell me ready or done. Ready, meaning you are ready to go through the solution because you didn't get the right answer, or done, you can tell me, hey, I got the right answer. I'm all done. I'm all good to go. So let's kind of go to, this was the problem that we had at the end of class. So there's the answers for part A and part B. Okay. So I'll ask you guys to try to work through solving part A and part B, and then I will look into the chat to see when you guys are ready. And at that point, we'll sort of start working through the solution. Okay, but I'm going to mute myself and stop my video, but I'm here if you have any questions. Feel free to unmute and ask questions if you want, but I'll just give you guys some time and space to work through the problem. I am going to stop sharing my screen here just so that I can work on a couple of problems that I have for us to work on in a little bit here. Highlighting that what you'll see here, this is problem 14. So on that skills sheet, and I think you both have access to where you can find those skill sheets. But moving forward, you'll be able to see those problems. So I won't necessarily always have this screen up.
So I'm a little stuck here trying to determine what order we're working with.
Got it? So yeah, let me go back. Let me start sharing my screen. I had talked about this, I think, at the very end of class, but it might be something if you were packing up or thinking about something else that I know I talked to a couple people, but maybe I didn't get a chance to kind of communicate to everybody. So let me share my screen again and highlight. This is one of those things you're not going to have to worry about for Wednesday, because it is something that I will tell you very clearly in a sentence, you know, first, second, or zero order. So for this problem, we get information about what order it is from here, okay? Units on the rate constant will tell us order. So units on K can give us order, okay? So see if this makes sense. I'm going to have rate equals my rate constant times the concentration of whatever my reactant species is raised to some power. That is the reaction order. Okay.
Mhm.
So what are the units of rate always going to be?
Moles over liters.
So it's going to be molar, but it's going to be moles
Over a unit of time.
Correct. So it's going to be molar per unit time. And let's just say here that since we see seconds here, I'm just going to put units of seconds. Okay. So this is always going to be equal to, they tell me that the rate constant has units of 1/seconds, right?
Mm-hmm.
And I'm going to be using that. I'm going to multiply by some concentration of my reactant. And I need to know how many reactant concentrations I'm multiplying together, because that will give me either molar with 1, molar squared, molar cubed, no molars. Okay. So
Mm-hmm.
can you see from this, how many molars do I have so that my units on my left and my right are going to be equal? How many molars do I want to have here? I need to figure out what my exponent is. Do I want my exponent to be a 1, to be a 2, to be a 0?
I don't know. I guess I'm not thinking at it right. So
Well, so let me ask a question. If molar, if this was a first order process, what would N be equal to?
N would be 1.
Right. So let's go through this. If N is equal to 1, then I'm putting a 1 in here. That means I'm only going to have 1 molar. I'm going to be multiplying molar times 1/second, which is what it tells me that the rate constant is. That's the units of the rate constant. And in that case, I'm going to have molar over second equals molar over second. My reaction is first order. Let me walk through and show you what would happen if we pretended to have this be second order. Okay, let me do the same thing. Rate equals rate constant times the concentration of reactant raised to a power that is the order. So if this was second order, molar over second, I always have molar over concentration over time is going to be my rate. 1/second. Now, again, I get this 1/second because it told me this. This was the units it told me of my rate constant. That's why I'm putting in 1/second. Okay. Now, if I had a second order process, okay, N would be equal to 2 there. And in that case, I'd have molar squared. In that case, I would have molar over second, and then it's molar squared over second. That does not equal. Okay. So what would I need the units of my rate constant to be? Charlotte. What would I need the units of my rate constant to be so that I still ended up with molar over seconds equals molar over seconds? What does this guy mean?
Oh, yeah. Are you asking if it was second order?
Yes.
So it would have to be molar squared, right?
Well, so I'm going to have a reactant concentration that's molar squared, but what do the units of my rate constant have to be? So that when I multiply the units of my rate constant times molar squared, I equal molar per second. Elias, can you see?
Would it have to be minutes?
Well, it's still going to be unit time. We're not going to need to worry about minutes, but the units of my rate constant are going to change because units of 1/2 for a second order process won't work because I can't multiply the units of my rate constant times 2 molars, molar squared. That doesn't equal molar per second. Okay. Does it make sense? I need to have something else in my denominator here. Do you see?
No, I don't know.
I need to have 1/2. I need to have a molar in my denominator of my rate constant units. Because then it'll cancel out with one of my molar squareds. And then I will have molar. I'll leave 1 molar in my numerator, and then I will have seconds in my denominator. And now my rate in molar per second will equal molar per second on the right.
Okay, I'm gonna have to study that more because for some reason that's the most confusing thing you've talked about in the past like 10 days to me.
Okay.
Sometimes I just need to like step back and approach it from a different angle, and then I understand.
So our rate constant is going to have different units depending on whether it's 0 order, first order, or second order. Okay. I have to multiply the units of my rate constant times a certain number of molar units. If it's first order, there'll only be 1 unit of molar. If it's second order, there's going to be 2 units of molar. If it was 0 order, there would be 0 units of molar. That's why this is molar to the first. This is molar to the second.
Okay.
Are you with me on that?
Yep.
Okay. So I need to figure out what do I need to have that I'm multiplying by molar squared so that I end up with units of molar per second.
Yeah, you got to have one of your molars cancel.
Yes. So that means I need to have units of my rate constant that have molar in the denominator.
Yeah, to give you that extra molar so that'll cancel out.
Yes. Okay. So this one is a bit trickier in the sense that you get what order the reaction is by looking at the units of the rate constant. So that's what makes this problem a little bit more challenging. You're not going to see that Wednesday, but move forward knowing that this is a second order process. Does that help?
Oh, so the one we have right now is a first order, and then the one we were talking about that.
Oh, I'm sorry. You're right. The one that we're working on right now. Yes, this is first order. This is a first order process. You're absolutely right. I got lost in my going through the other example. This is a first order reaction. If you saw this question on Wednesday, it would say for the first order decomposition of gaseous nitrogen pentoxide. Okay. So you will have in words, whether it's 0, first, or second. So this is first. Okay.
Yep.
All right, Elias, are you good to start working on this problem then?
Yep.
Okay, so you guys work on it. Let me know in the chat. There's a part A and a part B, so work on both parts. Let me know when you're done. Okay, I'm going to stop sharing my screen so I can sort of work on the solution for another problem. Elias, you still working?
Yeah, I was doing it like before you went over the units thing, and then I kind of got confused after that.
Okay, do you want some more time to work or are you ready to go through a solution?
Can we just go through it just to see
Sure.
how
Yep.
it goes?
Yep. All right. Let me flip back here. Sorry, my iPad is not happy right now. There we go. Okay, so I've got a lot that's on here. So if you want, like, take a screen capture of this, take a picture with your phone, just something so that maybe you're able to listen as I go through sort of the explanation, particularly if it was something that you got stuck on. Okay, so when we were talking before, we indicated that the rate constants units are where we're going to get the reaction order from. So come exam time, that's potentially something that could be part of a problem. Maybe it's like a part one type situation, just kind of saying, hey, rate constant for a process is this. What's the order for the reaction? So it's not necessarily going to be something that's embedded within another problem, but I do want you to know that the units of the rate constant will inform you about the reaction order. Okay, so once we know that this is first order, we're going to treat these problems all the same. I'm going to try, as we work through, this unit on kinetics and next unit on equilibrium, I'm always going to give you, like step by step, like these are the steps that you want to do. And if you use that sort of as a scaffold, hopefully it can allow you to sort of crawl through these problems if you find that you're getting stuck. Okay, so we know that it's a first order process. So that's the first step, is identifying the order of the process. Now for Wednesday's quiz, that's going to be given to you. So that's a problem you won't have to worry about. Now, once you know the reaction order, you have to pick out the equations that match it. So here is the equation for the integrated rate law for a first order process. We're not actually going to need it for this problem, but that is the corresponding matching half-life equation for a first order process. Okay, so now this problem tells us that the initial concentration of N2O5 is 1.58 moles per liter. So we want to know what's the N2O5 concentration after 5 minutes. So let's tackle part A first. You're not going to see a problem on Wednesday that asks you like a part A and a part B. It's only going to be one problem. And remember, I'm asking you one of four things. How much did you start with? That's going to be this piece. And notice that all of our equations have these same four parts. How much did you start with? How much do you have now? How much time has passed? And remember, if I ask the question, how much has reacted? Okay, that's the difference of these two, A sub 0 minus A sub t. Okay, so how I always like to solve problems that are equation based is I write down the corresponding equation and then I make a list of all the pieces to that equation. Okay, we have to make sure that things are in the right units. We look at stuff. So A sub 0 is 1.58 molar. A sub t is what we're trying to solve for. Okay, the time that's passed is 5 minutes. And then the rate constant is given as 2.8 times 10 to the minus third reciprocal seconds. Now, this is the first time we've seen a problem like this. The reason I like listing all of this together here, and particularly putting these two pieces next to one another, is you do have to make sure you check out that the units of your time that are given and your rate constant match, right? If you're solving for one of these two pieces, that means you're given the rate constant and you're given the amount of time. They're going to be multiplied together right here. So the units of time have to be the same. I'm always going to recommend that you convert the units of time into the same units as your rate constant. I'll show you in another problem. It can get really confusing if you try to convert the units of the rate constant instead of being reciprocal seconds, trying to convert that into reciprocal minutes. It's a classic case of students kind of inverting how they need to do their unit conversion. So I always suggest convert your units of time into the same units as your rate constant. Okay. Now, once we've done that, so that's going to be our time piece, we put all of our pieces into this equation. And Elias, I think you and I were maybe working on this in my office today when you came in for office hours. We're going to have the natural log of 1.58 over a sub t equal to our rate constant times the time that's passed. And again, we notice now that that's why we had to make sure we change the units of our time so that those units canceled. So this is going to be 0.84. So that's sort of the multiplication of those two guys together. And then we have the natural log of 1.58 divided by a sub t. So just like in, when you were in, I guess the other day, Elias, we kind of commented on this. The one time that you're going to need to use the E is when you have your variable that's unknown, part of that ln fraction, okay? So in this case, we're going to need to use E to break apart. And remember, when you have E to the ln of something, what you get is that something. So remember, Elias, we were in my office today and you actually took E to this number and then had that there. So I think now we understand that that's not what we want to do. This is what we're going to have. You were going to say something there, Elias.
I was just saying, yeah.
Yep. So, and I'm glad, I love when you guys kind of have a little bit of a wrong turn, because it's something that we can then address and make sure that other students don't, make that wrong turn and they understand how to do this math. A lot of what we do, there's like the chemistry part that you need to understand, but then there's the math part that you need to do. Often it's algebra or it's unit conversion that we're going to need to do. So now that we've got 1.58, that's the something, 1.58 over a sub t equals, and now when I take e to the 0.84, this gives me 2.316 and change. I like to keep 5 to 6 significant figures until I round at the end. Okay, solving for a sub t is going to be equal to 0.6821. Okay, rounding to 2 significant figures, because that's what I have here, 2 significant figures here, is going to give me a final answer of 0.68 molar. Now, if you rounded it to 1 significant figure, because somehow you looked at this, that's okay. So I always give you plus or minus 1. But sorry, Charlotte is growling here. I think she's got, what does she have, a bone? She's trying to get at her bone. Sorry, she's in her crate and she's just playing with her bone. The reason that temperatures are put in here is not that we're using temperatures, but there are parts of kinetics problems that have to do with temperature. We're not getting to those until Gen Chem 2, but it is important that we highlight that that rate constants are temperature dependent. Again, we'll get to that next semester. We're not doing anything with that now, but this isn't anything that comes into play with significant figures. So I'm going to pause at the end of that explanation for part A here. I'm going to see if you guys have any questions.
Nope, I'm good.
All right, Elias, you good?
Yep.
Okay, so the next part says, what fraction has decomposed after 5 minutes? So because the time is the same, this part is actually building on the first part that we did, okay? So it asks the question, what fraction? Anytime we think fraction, I want you to think part over whole. So what fraction has decomposed? So I want to know the part is the amount that's decomposed. The whole is the amount that I started with. Okay. So what I have down here is the amount that's decomposed, or the amount that's reacted, is the difference between what we started with and then the answer that we just got, the amount that's left. So I'm going to take the 1.58 molar that I started with, and I'm going to subtract the 0.68 and change molar that I have left. That's going to give me the amount that's reacted or decomposed. And then I'm going to put that over what I started with. And it'll tell me that 0.57 is the fraction that's decomposed. The problem might ask what percent has decomposed, and that way you'd say 57%. Okay, so not too much calculation to sort of do with that part. But you could have actually asked this problem, you could have done the part B without asking part A. You would have had to do the part A work in order to answer the part B question. So I'm going to pause there for a second and see if you guys have anything on this part.
I'm good.
Good. All right. So let's work on another problem. Okay, so I'm gonna, I'll give you guys a couple minutes here to write down the prompt. And then I'm gonna take down my screen sharing just so that I can continue to work on solutions for some future problems here. So this is an isotope of bismuth. They give us the half-life is 1.01 years. We wanna know what's the mass in milligrams of a 2 milligram sample that remains after 3.75 times 10 to the third hours. Okay, so I'm going to mute myself here. I'll let you guys work on it for a few minutes. In about 2 minutes, I'll stop sharing. So make sure to write down the prompt and the answer so you can let me know when you're ready. If you didn't get the answer, or let me know if you're done and you did get the right answer. Oh, awesome. I see you both said done there. So that is really great. So that means you got the right answer. So I'm still going to take a second and I will go through the solution here, so that if there's other people who are working through and watching this video later, they'll have an opportunity to kind of see what's going on. And I have a cat who's insisting on trying to come up and join here. All right, so remind me again, this was the problem we were on, right? And this is Finn. So Finn is very hungry and I think he wants dinner, but he's going to have to wait. So
I love your pets.
So this is the problem we were working on, yes?
Yep.
Okay. All right. So great. You guys got the answer. So let's kind of just walk through. Again, I always try to have the same sort of thought process for what we do here. In this case, I'm going to just move some stuff up here. This is the equation that we're going to want, right? This is the equation that we're going to want. And they give us half-life. And so we're going to need to use our half-life equation here in order to figure out what K is. And I'm noticing here, right, K is going to have units of reciprocal year, but my time is given in hours. Now you could go ahead and solve this problem using, you could convert the rate constant to units of hour. And actually I have this worked out here because this was a problem we did last year. And so I had students who had tried to do it and they weren't getting the right problem, and we identified what was wrong. So I am going to, I think it's on this problem. I'm going to show you what they had done, and then we'll sort out how you could sort of work through it. So we've got our equation here, our pieces that we have here. We know that we start with 2 milligrams, highlighting that it honestly doesn't matter what the units are for the amounts, okay? And even at that, I don't put those units in when I'm doing my calculations because they sometimes just get in the way. It doesn't matter what the units are for amount. Now we do have to pay attention the units of the rate constant and the units for time. Those are important, but the units of amount, because we're taking a ratio here of amounts, those units are always going to cancel out. So it really doesn't matter what the units are mathematically. Okay, so I'm trying to figure out what mass is going to remain. Okay, so that's my n sub t. And so then I can have my time here is hours. Now, because I have a mismatch between the time units that are given in hours and the time units of my rate constant, because my half-life was given in years, I do need to do some unit conversion here. So I, again, always find it easiest to convert the units of time that's given to whatever the units are for my rate constant. So in this case, my time that's going to pass, if it's 3,750 hours, is just under half a year, so 0.428 years. So that piece goes in here. My rate constant goes here. The amount that I start with is going to go here. And then I'm solving for n sub t. So this is another one of these problems where I need to use my e, because the piece that I'm interested in is part of a fraction that is an ln. So I'm going to take e to the ln of something. And so I'm left with something. So it's 2 divided by n sub t, what I'm left with, what's remaining. And then I have to take e to the 0.29 and change. So don't round until the end. And then you get that what I'm left with is 1.49 milligrams. So you guys got the right answer there. So I'm not going to take too much more time kind of going through this, but I do want to highlight, I guess it's going to be for another problem. I do want to highlight, because a student had asked for another problem. What do you do? Or like, they tried to actually convert the units of the rate constant to be units of hour. And so that is something you can do. It's a little bit trickier. But you will get the right answer if you do that correct. One other thing to highlight, and these are all different ways that I could just tweak problems to ask them a little bit differently. I might say for this problem, what amount of the sample has reacted after this amount of time? Okay, that's another way to sort of ask. I want you to be able to ballpark things too, right? So again, this is saying, half-life is a year. I've had, let's ballpark a half a year go by. So I've only gone through half of a half-life. So I should be more than 1 milligram left. I should be somewhere between 1 and 2 milligrams. Okay, so that's a way to ballpark and make sure that your math is right. Okay, I really encourage you, especially with the one quiz question. All right, Elias, no problem. Feel free. You can sort of watch more later if you want, or if you feel like you're good, you got this last problem right. Good luck, and I will see you on Wednesday.
All right, thank you.
You're welcome. All right, so, oh, Charlotte, just a minute. All right, so I think that's all that I was going to say for this problem. Any questions from you, Sarah?
Nope, seems pretty straightforward.
Okay, let's work on one more and then we'll see where you're at. I don't want to keep you longer. If you don't want to work any longer, what I might do is whenever you feel like you've had enough, that's fine. You can sign off and I'll probably go through the rest of the problems that I have. But I won't need to wait before I kind of walk through a solution for everybody. But let's take this next one. Half-life of radium is given as 1.6 times 10 to the third years. How many hours will it take for a 2.5 gram sample to decay to the point where I have 0.185 grams remaining? So I'll give you a minute to write down that prompt. Okay. And this is one of these problems. If you saw a problem like this on Wednesday, I would remind you that nuclear decay processes are first order, but come exam time, that's something I'm going to want you to know, that when we're talking about nuclear decay processes, they are first order processes.
Is first order more common? It seems like a lot of the stuff we're doing is first order.
That's a really good question. And I think you're right. As I was looking to try to find examples of zero order and second order, there weren't a lot of sample problems that had those. So I had to make some. And I think it is common, particularly for decomposition reactions, for things to be first order. But you know, we did lab. You already had lab this week. We're going to analyze the data next week. But maybe if you sort of like looked at what was happening in those processes, those were two things that were reacting. It's going to end up being first order for both of those processes, but overall the reaction is going to be second order. So, and we're not going to get to this until next semester when we start talking about more of like the theory behind kinetics, but we'll learn about what it really means to be a first order process or a second order process. It has to do with how many molecules need to bang together in order for chemistry to happen. So I think first order processes, or at least for processes that are decomposition processes, they are first order.
Yeah, I don't think we've even done a zero order equation yet in practice.
I think you're right. And you know, zero order, like zero order reactions aren't very interesting, right? Because what that means is I'm going to change the concentration of something and it's not going to change the rate. Now, it doesn't mean, you know, that like chemistry is not happening or things like that, but you're right. Zero order ones, they're a little bit hard to think about too, because it's like, what do you mean I'm going to change the concentration of something and it's not going to affect the rate?
Hi, so maybe you can help me here. Something's going wrong. Every time I'm trying to take the E to get rid of my log, I'm just getting an error message on my calculator. So I'm obviously putting something in wrong.
All right, why don't you, can you show your video to me and then you can show me what you're doing on your calculator?
Let me see if I can figure this out.
Yes, I
Oh,
see you
okay,
now.
here we go. So let's go ahead and flip this. Okay,
Perfect,
and so
yes.
this is what I'm doing, right? So I've got this, I'm trying to solve for the rate constant.
Okay,
Is that correct? I don't
let me,
No, stop.
actually, I gotta go back to this problem. So let me flip back. So point. So let's see. So T1 half, so you're gonna, so show me back and see that. So T1 half equals 0.693 over K. So to solve for what K is gonna be 0.693 over T1 half. So you essentially just
Oh,
like
yeah, okay.
swap.
Yeah, I don't
One
know why I
minute.
flip-flopped that.
Dad can help you. Okay, 1 minute. Put it in for 1 minute.
And I know that. I don't know why.
Uh-huh.
I'm gonna blame it on my husband. He's been talking about where his work pants are and all sorts of stuff while I'm trying to solve this problem, and I can't do math and other things at the same time.
That's okay. I've got an 11-year-old ask me about microwaving tortellini. That's what that was. He was like trying to figure out how long he needed to put it in the microwave.
You can probably do a little bit of math while you're having another conversation, though.
Maybe I have had a little practice in that. JT, are you gonna come feed Charlotte, please? I need somebody to feed Charlotte and CJ and Larry and Finn, and then I will get Larry in a second.
All right, I'm just gonna pause it since that's where I went
Yep.
wrong. I knew I was going wrong somewhere, so
Okay, I thought you had a question. Did you have a
Yeah.
question about E, or you're good now with E?
I'm good now. I was like, I know I did something wrong because I
Got
can't
it.
finish this problem.
Got it. Okay, so I'll let you finish and then we'll come back and look at the solution.
Okay. Okay, can you just go ahead and show me the answer? I'm
Yeah.
getting mixed up somewhere.
Okay. So back here. And this is problem 10. Is that the one we're working on?
Yep.
Okay. And guys, that can't be too loud right now.
Stop slamming that.
All right, so ignore the blue that's on the top right now. I'll talk about that in just a second. So half-life of radium is given as 1.6 times 10 to the third years. So we know that this is a nuclear decay process. So again, decay processes are always going to be first order. So again, I would have told you that for Wednesday's class, but I do want you to know come exam time that nuclear decay processes are first order processes. So that's the equation we're going to use. So
I already see what I did wrong.
what did you do wrong? Tell me.
I forgot to take E to the sum of 2.5 divided by 0.185.
Got it. Well,
'Cause
it's
I'm
not
used to
E,
just-
it's the natural log of that.
Yeah. So, okay. Yeah. So that's the part that makes me up because I am just used to like taking E and like getting rid of the log and doing it to the other side.
Yes.
So I guess
Yes.
it's good to like do another format where instead of solving for the, the resulting concentration, we're solving for time.
Exactly. So just to walk through, so if anybody else needs a walkthrough for this problem, this problem gives us the half-life. So we do need to use this equation to convert half-life into a rate constant. So that's how we're going to get rate constant here of this piece. So that's how we're going to get our rate constant that we're going to put in there. So, but you're absolutely right. We've been doing all of these problems where we need to use E because we need to break apart that ln of our variable kind of mixed in there. So in this case, when we put all of our pieces in, the amount that we start with is 2.5 gram sample. So that's going to be our n sub 0. And they tell us how much remains. It's 0.185 grams. So you're right. We need to figure out mathematically what this is. That's 13.5 and change. So then I take the natural log of that and I get to 2.6 and change. Now in this case, this kind of just carries down through. So the algebra for this one is actually a little bit easier when we're solving for time. Time is going to be equal to a little over 6,000 years. Okay. And, but the problem asks us to calculate the answer in hours. So this is a problem where we wouldn't need to do the unit conversion piece until the end, but our rate constant is going to have units of reciprocal years. The problem is asking us about time in hours. So we actually do that unit conversion piece on the back end. Notice I didn't round here yet. Okay. But then I'm going to convert years to days, days to hours. And then I'm going to have with 3 significant digits, because that's sort of what I have here with all my pieces, 5.26 times 10 to the minus 7th hours.
Yep, totally makes sense now. I should have
Oh,
just paid attention to what the equation was telling me to do instead of what I've been doing for the other ones.
And hang on a second, I think I have a minus there that I'm not supposed to, because this is going to be a long time, right? So if it's 6,000 years, that shouldn't be minus 7. So I apologize for that. Let me fix this. All of those people who, yeah, it's positive 7. I don't know how that negative kind of found its way in here. Let me get rid of that here. So hopefully as people are working through this problem, that's, I apologize because I probably had here, I'd had that minus there. So we're going to sort of fix it. It's going to be a little bit past the point for people who are kind of working through the problem, but that is a long time, not a very short time. All right, so that's that problem. So I don't know. I think you find another place where you got stuck, but clearly my answer, if you were trying to get to my answer was wrong there in that having that minus. So other questions, Sarah, or I'm going to kind of comment on a couple of other ways to kind of give you guys an idea of how I can permute problems, how I can make new problems from one that we've already done.
Yeah, no, that totally makes sense. I'm sorry. I'm like very distracted at home right now. So I'm
It's
kind of
okay.
making silly mistakes.
That's okay. So just highlighting, maybe if the problem, if the question was asked, how many hours will it take for a 2.5 gram sample to have 0.185 that decayed, right? Or 0.185 that reacted? Then I'd have to take the difference between 2.5 and 0.185 to get the amount that remains. Okay, so just another way that I could ask just a different flavor of this problem. So you do want to make sure, whether it's the quiz on Wednesday or the exam that we have in a couple of weeks here, you have to make sure you read the problem carefully so you know exactly what you're solving for. Does that make sense?
Yep, it absolutely does.
And I think this was a problem too, just because this was a problem I had worked through this solution last year. I'm just going to show this because there was a student who tried to work through the problem and they had actually not converted the time to, so the black in this problem is exactly what you see here. The red is mapping on. I had a student who actually converted the half-life. They wanted to convert the half-life to units of hours to start. So I want to show you how sort of that they did that. Okay, so then they went and they said, okay, I'm going to convert that 1600 year half-life to hours of half-life. That's going to be a lot of hours for the half-life if the half-life was 1600 years. And so this is just kind of working through. Then it's going to be putting that guy in here to get this in units now of reciprocal hours. So you can do that. But I often find it easier not to mess with the half-life or the rate constant, but to think about doing a conversion with the time piece. And so we actually did that where we did the unit conversion on the back end because we needed to get that into be units of hours and making sure to correct. This is not a minus here. So not a minus there. All right. Do you want to do another problem, Sarah, or are you a little bit spent?
I'd like to try one more and then I'll have to
Okay.
go.
So this is one of the problems we did in class today. So if you kind of look back at your notes, you'll see that this is a problem that we did in class. This was the problem where we had the answer in 7 seconds. Okay, so that was a part A to this problem. How long will it take for that concentration to reach 1/3 of its initial concentration? So that was 7 seconds. So I'm going to give you a part B on this problem, which actually builds sort of on it. And the part B says, what will the AB concentration be after 10 seconds? So I'm going to flip back here just so you can see the prompt again. So here's our equation, or here's our chemical equation. AB is decomposing. So the first problem said, how long will it take for AB to reach 1/3 of its initial concentration? So this doesn't necessarily build. We're not going to use answers per se from this problem, but now it's asking the question, what is the AB concentration after 10 seconds? So this is part A. So we're not going to consider this part. We're just kind of putting in the next part that says, if we have this decomposition reaction, rate constant or rate law is given. So we know that it's second order and rate constant is given. Now we want to know what's this concentration? What's the AB concentration after 10 seconds? Okay, so go ahead and try working on that problem. You should get an answer of 0.4 molar. Okay, so I'll give you a minute to work. Do you still have, I don't want to, because I don't have the whole prompt for the question. Do you have this one from your notes? Do you have this first part? Because this is the part that we need to kind of move forward.
Yep, I've got all that data. So the question is, what is the concentration of AB after 10
seconds?
10 seconds. Okay.
All right. So
Yep.
go ahead and work on that and let me know in the chat or just unmute since it's just you. Whenever you're done, we'll go through this solution and then you'll be good to go. I'm going to stick around and probably just walk through the solutions for some additional problems, just so that people can continue to practice if they want to watch some more solutions.
Okay, I got a 0.37.
Yep, that's right. And if we round to two significant figures, well, actually, I have two significant figures, and for some reason I rounded to 0.4. So yes, that is correct. So let's go ahead. Let me share my screen here, and we can look at the solution for this. All right. So this problem, again, this one was second order. So this is kind of doing a second order one. And you're right, we really haven't done any zero order ones. They're kind of weird. So for the most part, you're going to see problems that are first order and second order. And first order, I feel like, are the most common ones that we see. So second order process means we're going to choose that equation. Again, remember the ln stuff goes with the first order, the 1 over stuff goes with the second order, and then the one that doesn't appear to have any modification is the zero order. So using that equation and kind of putting all of our pieces in here, okay, we've got A sub 0 is 1.5 molar. We want to find what we have left after 10 seconds. So our time is 10 seconds. And our rate constant, remember we were talking about how many molars we have to have in our denominator. Just want to make sure that everybody sees this here, because this looks like it has units of liters per mole second. This is really the same as 1 over molar per second. Because if I've got molar in the denominator is moles per liter in the denominator, which is the same as putting that liter up top. Okay, because if I have liters in the denominator of my denominator, I can put it in the numerator. So I just want to make sure that everybody sees that those are the units that we'd expect. They're just written differently. Okay, and Sarah, did you say you did get this problem, right? It was just a matter of rounding. Okay.
Yep.
So put all these pieces in. You know, we're going to put in our K value right here. So let me just kind of go through and highlight pieces here. We've got our K value that's going to go in here, and then we're going to be multiplying it by the time that's passed. So there's our time. I don't have units that I wrote in here, but it's important that we recognize that even though there's some additional units in our rate constant of having a molar in the denominator, the units of time there are second, and the units of time that are given in seconds. So those match. So we're good to go there. And then it's just some algebra here. 1 over a sub t is going to stay as 1 over a sub t until we solve algebraically for it. 1 over 1.5 is 0.6, kind of repeating. That's what that line over the top means, is 0.66666. And then once we kind of combine like terms, so this is going to be 2.666. And then we can take 1 over both sides to isolate a sub t by itself. That's how we get 0.375 molar. And again, if I were to round to two significant figures, I would round to 0.38. Let me just kind of look back here. I think here's why we have one significant figure here, is our rate constant has units of 1 significant figure. And so that's where we're getting our 1 significant figure. So I'm going to change this here. It really is 1 significant figure because of the units of our rate constant, or I'm sorry, the number of significant figures in our rate constant. Good to go?
Yep. Thank you.
I'm going to keep recording here. I have a few more problems that I'll work through. So I'm going to go quickly through them. I'll pause for a second so that people can see the prompt. But then you can kind of choose to watch just through a work solution. So we'll see you later, Sarah. Thank you.
Thanks.
We'll see you. All right, so I'm going to go through these kind of quickly just so you could sort of see some more worked out solutions. Okay. Next problem here, a biochemist studying the breakdown of the insecticide DDT finds that it decomposes by a first order reaction. So again, this is how you're going to see things on Wednesday for your quiz. It's basically going to be telling you what the order of the reaction is. In this case, it gives us a half-life of 12 years. Remember, if you're given a half-life, that means you need to use the associated half-life equation to get your rate constant. So how long does it take DDT in a soil sample to decompose from 275, again, units? We don't need to worry about what those units are. That stands for parts per billion by mass. How does it need to go? How long will it take to go from 275 units to 10 units? So go ahead, pause as I work through these next problems. Pause it if you want to try working through it on your own, but I'm just going to pretty much go straight through and kind of talk about the solution. So with this problem, I want to highlight that one of the skills that'll be important for you to do, or I would encourage you to do, particularly on Wednesday's quiz, because you should have some time, try to estimate or ballpark what your answer should be. And this is going to be with the counting half-lives. So see if this makes sense. If I start out with 275 units of my insecticide, after one half-life, I'm going to have half that amount, so 137, right? So I keep going through and having the amounts that I have until I get to something that's less than 10. And then I count up the number of half-lives I have. And I say, you know what, if I only went through 4 half-lives, I would have about 17 units left. Going through 5 half-lives, I'm going to have just under 8 or just under 9 units left. Because I want to know how long it takes to get to 10, I'm going to be somewhere, I'm guessing, estimating my answer. I'm going to have somewhere between 4 to 5 half-lives that are going to pass. To figure out how much time that is, 4 half-lives just means I multiply 4 times how long a half-life is. A half-life is 12 years, so that's 48 years. 5 half-lives is going to be 72 years. So I'm ballparking that I should have an answer between 48 and 72. The answer is 57. So our estimating worked. So let's go through the math here, which is always going to be the same. Pick your equation based on the order of the reaction. They tell us it's first order. Write your equation down and then kind of tabulate all your pieces next to it and then solve for your unknown. Okay, so here's the equation that we're going to need to have first order reaction. Okay, so here's a sub 0, a sub t. Those are 2 pieces that are given. I'm interested in how much time will have to pass. And notice here, I don't have my rate constant. They gave me the half-life. So I need to do a little bit of work here to convert half-life into my rate constant. So that's what I've got shown in blue here. I need to use the corresponding correct half-life equation for a first order process to convert that half-life of 12 years into a rate constant of 5.7 and change times 10 to the minus second reciprocal years. Okay, now I'm ready to put all my pieces in. Natural log of the ratio of 275 over 10, that's what I start with and what I have now. Multiplying my rate constant times time. This is not a case where I see E. Anytime you're solving for time, we're not going to need to use E. I take the natural log here of 275 divided by 10. That's going to be 3.3 and change. I'm going to divide by my 5.7 times 10 to the minus second and change. And I get units here that once I round to 2 significant figures is 57 years. Okay, so that's that problem. Oops. I'm going to stop sharing for a second here, just so that I can go through. I thought I had a blank one in here. Let me put a blank one in for the next problem. So let's see here. There we go. All right, start sharing my screen again. 2 more problems to work through with you. Again, these are starting to get, it's not that they're necessarily more challenging, it's just they're more applied. And so they might look like they're more challenging, but keep in mind, they're really not more challenging. It just, how the information is presented to us is different. Okay, so there was an A, a B, and a C part to this problem. So I'm going to just kind of highlight for you. This is talking about aspirin decomposition. This first part is actually not something that we need for the part A of the process. So we don't actually need to worry about that part. We're talking about aspirin. So they tell us after 30 minutes, the compound reaches a maximum concentration in your blood of 2 milligrams per 100 milliliters of blood. Again, that's just the units. Here are the units that we have here. Okay, those are units. If the half-life for this breakdown is 90 minutes, what is going to be the concentration? And again, they're asking for the same units, okay, 2.5 hours after it reaches its maximum concentration. Okay, so pause for a second if you want to try working through this problem. Okay, here's the worked out solution. Okay, I know there's a lot here. I'm highlighting here This is information that we actually don't need to solve this problem. So we already kind of indicated that. It's a first order process. So we're going to use this equation. And they give us the half-life. So we know we're going to need to use this equation in order to get the rate constant, because the integrated rate law for first order processes has the amount that you start with, which they tell us is 2 milligrams per 100 milliliters of blood. We want to know how much is left after 2.5 hours pass. And again, the half-life is given as 90 minutes. And so when we do our conversion here to convert that into a rate constant, it's 7.7 times 10 to the minus third minutes. I always encourage you, take the time that's given and convert it into the units of your rate constant. So we're going to do a little unit conversion here to convert time into minutes. So it's 150 minutes. And then we just go and we put all of this in. So anytime you're solving for an amount, you're going to need to use the E part. So the natural log of 2 over a sub t. And notice I didn't put the rest of this in. I'm going to put this same part of the units in my final answer. So I'm just going to put the 2 in here. Okay. So here's my rate constant times time. And I like putting my units in here because that's make sure that I double check that my rate constant and my time are going to have the same units. It's really important. Okay. Multiply these two together and I get 1.55. And then e to the ln of something is going to be that something. E to the 1.155 is going to be this 3.17 and change. Algebraically solving for your a sub t, rounding in this case to one significant figure because that's all that we have here, and putting our units back in, it's 0.6 milligrams for 100 milliliters. Okay, so that's that problem. I have one more for you to try if you want. Again, I want to highlight that even though the problem looks like it's more complicated, maybe has like weird units or something, you know, it's different from those simpler problems where it's like, hey, here's a generic A plus B reaction or whatever. This is real world, right? This is asking us to think about that. Okay, so I'm going to give you, this is a challenging problem because we actually have to change and manipulate the equation that we're using. Because they're talking about bacterial growth, which means we're actually going to be increasing concentration. They tell us that it's a first order process, but when we're talking about growth versus decomposition, we actually need to change this equation. And this is not anything I would expect you to know, but I just wanted to highlight that this is a way to do the same kind of a problem, but with a little twist on it. So in this case, we're going to need to have a minus sign there. That's going to reconcile the fact that this is a growth process versus a decomposition process. So if you want, go ahead and try working through this problem using this different equation, okay? And I'm going to work through the solution with you in just a second. All right. So again, highlighting that don't worry about what the units are that they say, just understands that there's some value here that has some units for how they measure amount. It doesn't matter what those units are. We're just going to have the same units in our answer. Or in this case, the part A here asks us to think about what's the population density after 2 hours. Okay, so let's see here. Here's the equation that we're going to want to use. So they tell us how much we start with. We want to know how much we're going to end up with. Keep in mind, one of the things that we know based on the chemistry that's happening is this number is going to increase. It's going to be greater than 1,000 there, okay, because we're growing and making more cells. They actually give us the rate constant, but they tell us the time that passes is 2 hours. Noticing here that the units of our rate constant and the units of time that's passed are not the same. I encourage you, convert the units of time into the units of your rate constant. So I'm going to convert that to minutes. It's 120 minutes. And I'm going to go through and solve this problem again, making sure that I have that all important minus sign there. And that all important minus sign is going to mean that this number is going to be a small number rather than a large number. And so when I solve for a sub t here, it's going to be just shy of 67,000. Okay, so in this case, I'm going to have 6.6 times 10 to the 4th cells per liter. Truthfully, this should probably be 6.7. Let me actually round this a little bit better there. Whoops, that's way too big. 6.7 if I round this properly. 6.7 times 10 to the 4th cells per liter. Okay. And you know what? I didn't actually work through a solution yet here for part B. So if you want, go ahead and try part B. Let's see, do I have the time here? I do have the answer. If you wanted to try working through part B on your own, I actually don't have a solution worked out here, but I will tell you what the answer is. So the answer for part B is going to be 20 minutes. Okay, that's how long it will take to go from 1,000 cells to 2,000 cells. So if you want, see if you can work that one through and get 20 minutes. Apologies, I don't have a solution worked through yet for that. All right, that's it. That's all I had for today. And I will see you guys on Wednesday.